Sum and integral representation for polylogarithm function. So basically in my previous video I've given idea about why this definition of polylogarithm makes sense, like how to connect this with the polylogarithm word, like how it's related to logarithms or to zeta functions as well, and about the special case when s equals to 2. I have told about those things in the previous video and I will link the video over here. Now in this video, let's try to prove this integral representation. So basically considering this sum as the definition, we will try to prove the integral representation of digamma function. And do note that for this sum to converge in real numbers, the modulus of g should be less than 1. Yeah, that is it. Now let's try to find the integral. We have 1 by gamma of s, integral from 0 to infinity, t to the power s minus 1 by e to the power t by g minus 1 dt. Now what we can do is we can basically try to take g as the LCM. For LCM we have g times e to the power t minus g dt. Now if we multiply numerator and denominator by e to the power minus t, you will get integral from 0 to infinity of t to the power s minus 1 g e to the power minus t by 1 minus g e to the power minus t dt. Now t is a positive number because t is going from 0 to infinity, and g is also less than 1. Its modulus of g is less than 1. So that's why the modulus of this whole expression is actually less than 1. That's why we can use the infinite geometric series since it is in the form of a by 1 minus r. So we will convert this into a sum now. We have 1 by gamma of s, integral from 0 to infinity t to the power s minus 1, and then sum going from n equals to 1 to infinity g e to the power minus t to the power n. We can note that the first term is g to the power minus t as it's here, and the ratio is also the same, because those are same. Now since t to the power s minus 1 is constant, we can take it inside the sum and then swap the sum and integral. That gives us sum from n equals to 1 to infinity, integral from 0 to infinity t to the power s minus 1 g to the power n e to the power minus n t dt. Okay. Now since the integral is in the world of t, g to the power n is a constant. So we can take g to the power n outside the integral into the sum. Now in integral we have t to the power s minus 1, we have t to the power s minus 1 and e to the power minus n t dt. Now this is just a special case of, general case of gamma function, or also about Laplace transform. And this is a special integral, a well-known integral, and the answer for this integral is gamma of s by n to the power s. Now you can see that gamma of s can be taken out since this is just a constant, because sum is in the world of n and this is in the world of s. And we have sum from n equals to 1 to infinity g to the power n by n to the power s, and there's a nice cancellation, and we get the sum of the polylogarithm function. G to the power n by n to the power s, which is lis of g. Okay, so this proves the integral representation for polylogarithm function, and note that this also involved quite a bit logic, because we had to know what is less than 1 and how to use geometric series. And okay, so we have proved both the integral and sum representation. Actually the sum is just definition. And if you haven't watched my other video where I described how when s equals to 1 this expression is just minus ln of 1 minus g, which is logarithmic function, and when g equals to 1, this is just Riemann zeta of s, yeah, and when s is 2, we call this as logarithm function, yeah. And such functions are important because they can be seen in many integrals, and if their properties are known, yeah, the integrals are really simplified, and yeah, this does help. So I think this is about the today's video. Like, I have tried to give you the proof of the integral representation, yeah, and hope to see you in the upcoming video where we will discuss the properties of the polylogarithm function under integration and differentiation. Thanks for watching. Look forward to seeing you in the upcoming video.